Okay, this is video 1.2, the second video from Unit 1. And we are still going to be dealing with limits today. And I just want to remind you of the definition of a limit real quick. Okay, so right here, this is from yesterday's notes. Limit, the final, utmost, or furthest boundary. That's from the dictionary. But then I added this to it. Think of it as a number we can always get closer to but never pass. Okay, so we're going to be dealing with that today. We're going to look at limits of functions by using tables and by using graphs. Okay, so here we go. Given the following piecewise function, that's a mistake. Actually, only the last one is piecewise. Use a table of values to determine the left-hand limit. The left-hand limit is the limit is the limit of the outputs as the inputs approach a certain value from the left. So you'll know what I mean in just a moment. All right, so here it is. We've got this function x minus 8 to the fourth, and we are finding its limit as x approaches 6 from the left. So the way that you would read this in words is the limit as x approaches 6 from the left, the little negative means from the left, of the function x minus 8 to the fourth. Okay? So the way you do it, guys, is you take a bunch of inputs that are approaching, that are getting closer and closer to 6 from the left, and then you look and try to find a pattern for those outputs that correspond to those inputs. Another way of saying inputs is x values, outputs y values. Okay, so I'm going to draw this number line. I'm approaching the value 6, and I'm approaching it from the left. So think of a number very close to 6, but to the left of it. For example, 5.9. Now think of a number even closer, 5.99. A number even closer, 5.999. So if you keep adding nines, you get closer to 6. So those are the three values I'm going to use in my table here. So I'm going to think of 5.9, 5.99, 5.999. And when I look at these inputs, which are getting closer to 6 but are to the left of 6, they're going to correspond with a set of outputs, and I'll be looking for a pattern for this set of outputs, and if I can find a pattern, that will be the limit. All right, so the way I'm going to do this is I'm going to take my calculator, and I'm going to use the table function. I cleared it. I'm going to go to y equals. I'm going to graph the function that I'm working with. Parentheses, x minus 8, close parentheses, raised to the fourth power. And I'm going to use my table function, but if I go to the table right now, they chose the x values for me. That means that my table is set at something I don't want. So I'm going to go to table set. All right, so the independent variables, which are the x values, are set to auto. That means the calculator will just choose them. I want to choose them myself, so I'm going to set it to ask. All right, now I go back to my table and I have a blank slate, and I'm going to type in these three x values here. 5.9, 5.99, 5.999. Okay, I got those values. I'm going to record them. I've got 19.448, 16.322, 16.032. And if at any point you feel that I'm going too fast, please pause the video, rewind it, any of that stuff. Okay, so as my x, now I'm going to do an arrow diagram. I'd like you guys to do this. Eventually we won't use arrow diagrams, but when we're first learning limits, please do. The x's are getting closer and closer to 6. They are approaching 6. So as x approaches 6, but from the left, the y values are approaching what? So this is where you want to think about this definition from yesterday. Is there a number within our y values that we're looking at that we can always get closer to but never pass? All right. So here's my set of y's. If I look at them, they are getting closer and closer and closer to some number, but they're never going to pass that number as long as my x's are to the left of 6. And what is that number? It is 16. All right, so as x approaches 6 from the left, the y's are approaching 16. All right, as long as my x's are getting closer to 6, my y's are getting closer to 16, but they're not going to pass it as long as I'm to the left of 6. Okay, guys, so the answer is 16. The limit as x approaches 6 from the left of x minus 8 to the 4th equals 16. Okay, 2 more examples, and then we're going to have a back page also. Okay, so here's the next one. The limit as x approaches negative 7 from the left of the function x squared over x plus 7. All right, so just, you guys might not feel the need to do this, but I'm going to do a little number line just so I can imagine the x values to the left of negative 7, okay? X values to the left of negative 7, let me think of one, negative 7.1. That's pretty close to negative 7, but to the left. Another one is negative 7.01. Another one is negative 7.001. So if I keep adding zeros in front of the ones, I'll get closer to negative 7, but I'll still be to the left of it. So negative 7.1, negative 7.01, negative 7.001. And now I'm going to do the same thing I did before. So here's my calculator. I'm plugging in my function. I've got x squared over x plus 7, close parentheses. I'm going to my table. All right. Now I still see all my old values, but that's okay. I can just type right on top of them. So I'm going to type those values in. Negative 7.1, negative 7.01, negative 7.001. All right, and I'm going to record those down, and then we'll talk about what they are telling us. So we've got negative 504.1, negative 49. Negative 4,914. My bad. Sorry, guys. I was thinking of something else while I was writing. Okay, negative 49,014. Okay, so as x approaches negative 7 from the left, are the y's approaching some value? Is there some number that they're getting closer and closer to but not passing? And the answer is no. Guys, for every little jump in x, I get an enormous jump in y's. Okay, and there's like no number that they are tending toward. So if I plug in negative 7.0000001, I'm going to get a huge negative number, like negative 1 billion or something. All right, so these y values, they're actually approaching negative infinity. All right, they are never going to stop getting more and more negative. All right, so the answer, guys, there's actually 2 ways you could say the answer. You could say the limit does not exist, there is no limit, or you could say negative infinity. I'm going to say negative infinity. If you have a hard time drawing infinities like I do, you could just do like 2 circles next to each other. I kind of like that. All right, now next, this is a piecewise function. The limit as x approaches negative 1 from the left of g of x, where g of x is defined in 2 pieces. It's x squared when x is greater than or equal to negative 1, and it is the line 2x plus 3 when x is less than negative 1. All right. Well, guys, which of these pieces is going to correspond to the values to the left of negative 1? The answer is this one, for the x is less than negative 1. All right. So here's a number line. If you don't feel the need for drawing a number line, you don't have to. But I'm approaching negative 1 from the left. Okay, so for example, negative 1.1 is very close, negative 1.01, etc. Negative 1.1, negative 1.01, negative 1.001. All right, and I'm going to use my calculator again. I'm going to be plugging in 2x plus 3. 2x plus 3, whoopsie, 2x plus 3. There's my table. Negative 1.1, negative 1.01, negative 1.001. All right, and I'm going to write down those y values, and then we'll talk about what they mean. 0.8, 0.98, 0.998. So as x gets closer to negative 1 from the left, that's important from the left because we also could be getting closer from the right, the y's, does it look like there is a number that we can always get closer and closer to but never pass? The answer is yes, and that answer is 1. All right? So the limit as x approaches negative 1 from the left of this function g of x equals 1. All righty. Now I'm going to turn to the back. All right? Guys, we're going to be doing a very similar thing here, but we're going to be using graphs instead of our calculators. Now, when I'm writing a table of values, I'm just going to be estimating the y values, okay? So if you choose at any point to pause this and try to do it on your own and go ahead of me and then check back with me, you may find that we are having different y values, but that's okay as long as we're close. Okay, here we go. The limit as x approaches 1 from the left of the function f of x, there's its graph right there, we're going to figure out what that is. So I'm going to choose x's very close to 1 but to the left. For example, 1 or 0.9, 0.9, 0.99, 0.999. Let's just keep getting closer. All right, so I've got this set of x values which corresponds to this set of points on the graph right about here, and those points on the graph correspond to this set of y values very, very close to negative 1. All right, so 0.9, guys, is that x value has the corresponding y value which is very close to negative 1. Okay, but like right below it. So I'm going to say negative 1.1. I am estimating. 0.99, that x value corresponds to a y value still below negative 1, but even closer. So I'm going to say negative 1.01. And then 0.99 corresponds to another y value below negative 1, but even closer than the other two. So negative 1.001. Alrighty. So as the x values approach 1 from the left, my y values are approaching negative 1. So the limit as x approaches 1 from the left of f of x is negative 1. All right. If you feel like you've got this, go ahead of me, and then at the end, just check and make sure we have the same stuff. The limit as x approaches 7 from the left of f of x, we're going to figure that out. So here's the graph. There's 7. Notice there is a vertical asymptote at x equals 7. Okay, so this is going down, 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 down. So this is an asymptote here, guys. It's going down. It's decreasing very, very fast the closer we get to 7. And if you look to the right, guys, it's also an asymptote on the right. Okay, but we're only caring about the limit from the left, or the left-hand limit. Okay, x value is close to negative 7, but to the left. 6.9, 6.99, 6.999. All right, now I am estimating the y values, the outputs. These are very gross estimates, okay? 6.9. Super, super close to 7. Guys, that y value, that's going to be like off the page. It's going to be like, if you're super close, 6.9, really, guys, we can barely even see that with our eyes. That's going to be very low, that y value. So I'm going to estimate 100. This asymptote, this graph is getting negative very, very fast. It's very steep, and it gets even steeper the closer we get to 7. So I'm going to just estimate that the y's are growing by factors of 10. So I'll estimate that this y value is 1,000. I'll estimate that the next is 10,000. And I can see that as x is approaching 7 from the left, Oh, these are negatives. My bad. Sorry, guys. Those should be negatives. The y's are approaching no particular number. They're just getting more and more and more negative. So negative infinity, just like the one on the front. All right, so the limit as x approaches 7 from the left of f of x equals negative infinity. Okay, we've got two more. So number 6, x is approaching 5 from the left. So I'm looking at this graph here. To make my life easier, I'm going to go to the x value 5. I'm going to find the point on the graph that corresponds to it. And that point, its y value is very close to 7. I'm going to estimate 6.8, okay? You could estimate, oh my bad, all right, so this is 5 comma 6.8. I'm estimating that for this point here. Okay, I'm getting closer to 5 from the left. 4.9, 4.99, 4.999. And guys, you can see as my x values get closer and closer to 5 from the left, my y values are getting closer and closer to the y value of that point, which is 6.8. So I'm going to be getting closer and closer to 6.8. So I'm going to estimate for x 4.9, the y is very close to 6.8. So I'll estimate 6.79. For a y value of 4.99, even closer to 6.8 for the y, or for that x, the y is even closer to 6.8, so I'll just add another 9, etc. So as x gets closer to 5 from the left, y gets closer to 6.8. Darn it. 6.8. Okay, so as x approaches 5 from the left, y is approaching 6.8. So that would be the limit. Last one. X is approaching -1 from the left. This is a piecewise function. I'm approaching -1 from the left, so I'm only dealing with this part of the function, which is the graph of a constant. It's just a horizontal line. Approaching -1 from the left. -1.1, -1.01, -1.001. This is a constant function. So no matter what my x value is, the y value is always the same. It's always 1. All right, so all of these y values are 1. So y is not approaching something as much as it is maintaining itself, and it's 1. So as x approaches -1 from the left, y is approaching, we're going to say it approaches 1, but really it stays 1. So that's another way that you could have a limit. So the limit as x approaches -1 from the left of f of x equals 1. Okay, guys, this video was 18 minutes long. It's kind of on the long side. The homework from the homework packet is just basically the same length as these notes. You will do it a lot faster than I did because I was like talking it through and going slow. So in your homework packet, where did I put mine? Here it is. In the homework packet, your homework is going to be pages 4 and 5, the entire things, 4 and 5. And then I'm just going to give you 2 problems on page 6. On page 6, guys, I'd like you to do just number 12. Okay, why don't you just do number 12 on page 6? Okay, so homework, pages 4 and 5, the whole things, and on page 6, just number 12, and you're going to want to use the formulas at the top to figure that out. Okay, guys, see you tomorrow.